Okay, welcome. So remember, we're in the middle of our discussion about different ways in which Fourier series can converge to a given function. So this is a problem that arose when we were looking at certain boundary value problems for partial differential equations on finite domains. And so for the last two lectures, we went into detail about one very important notion of convergence, which is known as mean square or L2 convergence. And in particular, we specified to the scenario where you're on the interval between minus pi and pi, although the theorem will hold more generally if you instead look at minus L to L. You just have to make suitable changes to take into account this change. And so what does the theorem say? Well, the theorem says that if you have any function which is square integrable, meaning the integral of absolute value of the function squared is finite on this domain, then if you look at the partial sums for the Fourier series from minus n to n, these will converge to the function in the L2 sense or the mean square sense, which means if you look at the norm of the difference, then the norm of the difference converges to 0 as n goes to infinity. And so this is kind of like the distance between these two separate functions, right? On the one hand, I have the partial sums, which is a function. And on the other hand, I have my function f. And I'm looking at the distance between these two functions in this kind of integral sense, right? And we want this to go to 0. And right, remember that here, en is defined as e to the inx. It's the complex exponential, right? Right, and so we saw throughout the course of the argument that really the important thing that makes everything work here is this notion of orthogonality. And one way to analytically take advantage of orthogonality is introducing these inner products, which played a big role in the proof. Right, and so we also saw the following. So as a consequence of the proof, we also have something that's called the Parseval theorem, which says that, okay, let's look at the L2 norm squared of my function, which is just the integral of the function squared. Well, then this is equal to the sum from n equals minus infinity to infinity of the Fourier coefficients of my function squared. All right, so these are the Fourier coefficients. And so there's actually a more general version of this result, which will hold for any orthogonal system of orthogonal functions, not necessarily these complex exponentials, but maybe other systems like the cosine nx terms, which we saw were orthogonal a few weeks ago, or the sine nx terms, which we saw were orthogonal a few weeks ago. So this theorem and the corresponding convergence result will both hold for these types of systems of functions as well, as long as there somehow are enough of them. And so in order to make this more precise, we would have to use more advanced topics than what we're dealing with in this class. So I can't go too much into detail here. But one thing which is a useful result is that if you look at all the eigenfunctions for a certain boundary value problem, as we did a few weeks ago, with 0 boundary conditions, or for example, Dirichlet boundary conditions, and you consider all of the eigenfunctions at once, for example, the cosine nx functions or the sine nx functions, you can define an analog of the Fourier series by replacing en here by those functions, and then you have a similar convergence result and a similar Parseval theorem, which will now hold with say xn, cosine of nx or something, in place of the complex exponential. So there's some more discussion about this in the book, which I would recommend looking over a little bit, although I'm not going to go too much into detail about this in the lecture. One thing I do want to comment a little bit more on, though, in more generality, is the following. So a generalized version of one side of this result. And so remember that in the course of the proof, we proved something called Bessel's inequality, right? And so Bessel's inequality is just an inequality which is related to the above formula. And so this says if you look at n equals minus infinity to infinity of the sum from n equals minus infinity to infinity of the Fourier coefficients squared, that this is always less than or equal to the L2 norm squared, right? And so of course, Bessel's inequality in this way is a consequence of Parseval's theorem, right? It's actually, what we have here is stronger. They're not just, it's not just less than or equal to, they're actually equal to. But remember, this was Bessel's inequality was a lot easier to prove than the Parseval theorem, right? And so this is, of course, this is stronger, but the Bessel inequality was easier to prove. And so Bessel's inequality also has a more generalized version, which is useful and which we're going to use later today. And so let me just review what that is. So let's suppose I consider functions not necessarily between minus pi and pi, but on some interval between a and b, where a and b are given. Well, we can define a generalized version of the inner product, right? So let's say f comma g. I'll use like say a comma b here. Although, I mean, from context, it'll be clear what your domain is, so you can usually omit this from the notation. And so this is 1 over the length of the interval, which is b minus a, times integral from a to b of f of x times the conjugate of g of x, right? And so you can similarly define the norm, right? Say the norm squared of a function, say between a and b, is just the inner product of f with itself, right? So that ends up being 1 over b minus a, integral from a to b of absolute value of f squared. Right, so these are just the same definitions that we've been working with for like 2.5 lectures, or 2 lectures. But now I'm not just looking at minus pi to pi, I'm looking at any finite interval, right? And you can redefine your inner products and your norms in the same way. Now let's suppose I'm given some collection of functions. Right, so suppose I have some sequence of functions, which you want to think of as like the complex exponentials, but they could be something else. They could be like cosine nx terms, sine nx terms, or some other sequence of functions. And suppose that we have the certain orthogonality properties. Right, and in particular, suppose that if I look at the inner product of xn and xm, that this is 0 if n doesn't equal m. And so in this case, we have a more general version of the Bessel inequality. Why is it more general? Well, these en are a special case, right? Of course, the ens have this relation, which was the crucial tool in proving the L2 convergence. But if you have a more general system of functions like this, then you have, if you look at the sum from n equals minus infinity to infinity, and I look at the inner product of a function f with one of these things, this is kind of like a generalized Fourier coefficient, and I take the square, that this is always less than or equal to the L2 norm. So right, this is on AB. This is always less than or equal to the L2 norm of f on AB. Right, and so in particular, if you know your function f, if you know that this integral is finite for your given function f, then this series always has to converge, and it always has to be smaller than the L2 norm of f, right? And so here we were looking at these generalized Fourier coefficients, take inner product of f with one of your orthogonal functions. Okay. And so this is also usually referred to as the Bessel inequality. And so it's proved in exactly the same way, right? So you look at the difference between the function and the partial sums, and you show that that difference is orthogonal to the partial sums itself, and you deduce this as a result. I think I mentioned this in a previous lecture, so if you go back to that lecture, you'll see a more detailed argument. I'm just reviewing this now because I think it'll be useful, or not I think, because it will be useful later in the lecture. Okay, and so now what we're going to do, that was a recap of the last week of class. Now what we're going to do is turn towards pointwise convergence of Fourier series, right? And so the L2 convergence, or the mean square convergence, is interesting, but for a lot of purposes, you really want your Fourier series to converge in a more natural, like pointwise sense, right? Like you want to say that the series that you're given is actually equal to your function at every single point, not this like weird L2 type convergence. And so we want to study this problem now. Right, so we will consider the following problem. So the question is, well, when does the partial sums for the Fourier series converge to the function? Remember, this means you look at the function f of x, you look at the difference between f and the partial sums for the Fourier series. And so the question is, when does this converge to 0 as n goes to infinity for each x? Right, so this is exactly what we mean by pointwise convergence. Again, it's like the more natural notion of convergence, where you look at the difference of your function and the sequence of partial sums. And we want to say that this sequence of partial sums for each fixed x will converge to the value f of x. And so this is exactly what it means for it to converge for each f of x. Right? And so we're going to prove the following theorem. And in this case, we will actually prove the theorem. We're not going to sketch the proof. We'll do all the details. So suppose f of x, let's say we'll again restrict to minus pi to pi. So suppose this function is differentiable and f prime is continuous. Then you do have pointwise convergence of the Fourier series. Right, so then the Fourier series of f converges pointwise to f. In exactly the sense I have above here, right? So for each fixed point, the sequence of partial sums will converge to the value of the function. And so this means that the Fourier series is indeed equal to your function. And so when we go back to the boundary value problems, we can actually solve them explicitly. The solution will be given by a certain Fourier series, and these are equal to the initial data as we wanted. As long as your initial data is quote unquote smooth enough, meaning you can differentiate it and the derivative is a continuous function, right? For example, like some exponential is a case which would work, like e to the x plus 4 x squared or something like that. That would be an example that works. Okay, and so we're going to begin with the proof of this. It's going to take a little bit of time to develop the necessary tools, but it'll be a little bit shorter than the discussion of L2 convergence. And so what I want to begin with is kind of like a auxiliary result, which we will use and which is also important for in other contexts. And so I briefly want to talk about a uniqueness result. Right, so uniqueness of Fourier series. And so this is the uniqueness theorem. Well, let's suppose we have two functions. And let's suppose that I call f with a hat n the nth complex Fourier coefficient of f. And say g hat of n is the nth, excuse me, complex Fourier coefficient of g, right? For example, what do I mean by this? Like f hat of n is 1 over 2 pi integral minus pi to pi f of x e to the minus I n x dx. As before, I'm just changing the notation. Right, so we're supposing we have two functions and we're going to label the Fourier coefficients in this way. The theorem is that, well, let's also suppose that they're both equal, right? If the nth Fourier coefficient of f is equal to the nth Fourier coefficient of g for all n, meaning the functions have the same Fourier series, then the functions have to be equal. Right, on the domain. Right, so again, this is a uniqueness result because it says if I have two functions and all the Fourier coefficients are the same, then the functions have to be equal to one another. Right. And so this is an important result for the theory that we're discussing because, I mean, it could be problematic that, right, so maybe, I mean, if we want to show the Fourier series converges to a function, well, maybe if we calculate all the Fourier coefficients for this function, maybe the series will converge, but it could converge to a different function, right? And this is an issue. And so this uniqueness result prevents that from happening, right? This is the role, and we'll use it in the course of the proof at a certain point, right? And so how do you do this? Well, it's going to actually follow from the L2 convergence results, which we already saw. There are also more elementary ways to prove it, but which take a little bit more effort. So what I'm going to do is define a new function, h of x. This is going to be very similar to the uniqueness results we saw for the diffusion equation using the energy method, right? So I'm going to define, or the maximum principle. So I'm going to define h of x to be the difference between f and g. And what I want to do is show that h is equal to 0 for all x. Right? And so, well, let's compute the Fourier coefficients of h, right? Right, so by definition, this is 1 over 2 pi integral minus pi to pi of h of x times e to the minus I n x, but h of x is the difference of f and g, right? So I can write this as 1 over 2 pi. Let me break up the integral. So I have one piece, which is f of x e to the minus I n x dx, and then I have the other piece corresponding to minus g of x times e to the minus I n x. But by definition, these are respectively the Fourier coefficients of f and g, right? So this is f hat of n minus g hat of n. But we're assuming, right? So look up here, we're assuming that these are equal. And well, if they're equal, then the difference has to be 0. So this is equal to 0 for each n. Right? And so it suffices to prove the following. If the Fourier coefficient of h is 0 for all n, not some n, but all n, then h of x is equal to 0 everywhere at each point. Right, and so this is what we'll prove now. And so this is going to be a consequence of the Parseval theorem, which I reviewed at the beginning of the lecture. I guess we should assume that the norms of these functions are finite. Sorry, as an aside. And okay, well, if you have a sum of two functions with finite norm, then the sum will also have finite norm. I'll skip that detail, but it's not too hard to check for yourself if you just use the definitions. Right, and so assuming that h has finite norm, well, we know that the Fourier series of h will converge to h in the L2 sense, right? Or in the mean square to h of x, or to h, right? But what is the Fourier series of H? I mean, all the Fourier coefficients of H are equal to 0. And so the Fourier series is just 0, right? So let's look at this. Right, so if we use this result, we know that if I look at integral from minus pi to pi, and I look at h of x minus the partial sums of its Fourier series, that this converges to 0 as n goes to infinity, squared, sorry. Right, so this is the L2 convergence. But each of these are 0 by the calculation we did above, right? And so if each of these terms is 0, that means the sum of them is 0. And so this implies that if I look at integral from minus pi to pi of h of x minus 0 squared, that this converges to 0 as n goes to infinity. But h of x minus 0 is just h of x, so I can just replace that by h of x, right? And well, the only way for this to be possible is if the integral of h of x squared is just equal to 0. And so this tells you that integral minus pi to pi h of x squared dx is equal to 0. But then we've seen this result before, this type of argument before in all these uniqueness arguments. If the square of the function is equal to 0, the only way this can happen is if the function is actually equal to 0. Right, so this says that h of x is equal to 0, right, which is what we wanted to show. Right, so this is like a special case of the vanishing theorem. And so in particular, well, remember h was equal to f of x minus g of x equals 0, and so f is equal to g. Right, so that's the proof of the uniqueness result. Okay, and that's an important and useful result, kind of an aside to the theorem that we introduced beforehand, but we'll see soon where this uniqueness result is used. And so now what I want to move forward and start talking about proving the pointwise convergence theorem. Okay, and so what are we looking at? Well, as before, I'm going to let f hat of n equal the Fourier coefficient just to simplify the notation a little bit. So this will be denote the nth Fourier coefficient of our function f. And well, we're looking at the difference between my function f of x and the partial sums for the Fourier series, which I'm going to write this way. Okay, and we want to understand when this converges to 0 as n goes to infinity. And so to simplify the notation a little bit, I'm going to let this denote s sub n of x for the partial sums. And so well, let's try to understand this function s sub n of x a little bit better. Right, and so let me try to calculate the Fourier coefficients of this function. So I'm again going to use the hat notation. So let s sub n of m with a hat on it denote the nth Fourier coefficient. Well, let's look at these coefficients. Well, you can calculate that. We can calculate this explicitly. So let's look at. Sorry. Let's use the inner product definition. So this is equal to the inner product now of Sn with E sub m, right? Where again, E sub m is e to the imx. So if I plug in the definition for Sn, this is the inner product of the sum from minus n to n of f hat n en comma em, right? But as we saw before, this is I'm going to skip some of the details, but hopefully these calculations are a little bit more familiar from the last two lectures. If you plug in the definition of what this inner product is, you can see that this is equal now to the sum from n equals minus n to n. You can factor out the f hat n's because they're constants, and then you just have inner product of en comma em, right? And so here this n is ranging between minus capital N and capital N, right? Well, remember that if I look at the inner product of en with em, this is only 1 if n is equal to m, and so it's 0 otherwise, right? Well, I'm holding m fixed, and I know that little n is in the range between negative big N and positive big N, right? And so, well, let's suppose as a first case, let's suppose that m is in the same range, right? Well, if m is in the same range as the sum over here, then there's exactly one choice for which this inner product here will be non-zero, right? So in this case, our sum is equal to just f hat of m, right? So this is the case when n is equal to m, right? What happens if m is outside this range, meaning the absolute value of m is strictly bigger than n? Well, in this case, E sub m is orthogonal to every single one of these, right? Because m is not in the range between minus capital N and big capital N, positive capital N. And so each of these inner products is 0. And so in this case, we're just going to get 0, right? And so what this calculation shows us is that what are the Fourier coefficients of our partial sum? Sorry, let me give myself some more space. Right, so this shows that if we calculate the mth Fourier coefficient of the partial sums, that this is equal to the Fourier coefficient, the mth Fourier coefficient of f, if m is between minus n and n, and 0 otherwise. Right, so it's 0 if absolute value of m is bigger than n. Right, and so what we've done here is, well, okay, we're trying to show that these partial sums, this S sub n, will converge to the function f. And so what we've done in this little digression here is just calculate the Fourier coefficients of this function here, right? So I can fix capital N, and I can view this as just a function of x. And so the question is, what are the Fourier coefficients? Well, you can kind of just see from inspection what they are, right? So you have these coefficients here in the range between minus n and n, and the coefficient at spot little n is just f hat of little n. And then, well, once you're outside this range, there are no more Fourier coefficients, so they should be 0. And what we've done here is just rigorously prove that that's the case, right? So that's what this formula tells us, right? Okay. And so now what I'm going to do is also introduce a different object. Again, this will seem like another digression, but I'm going to put the two ingredients together, and then we'll be able to use these two facts that I'm discussing here to proceed with the proof. Right, and so I'm going to introduce something that's called the Dirichlet kernel. Dirichlet is a mathematician who did a lot of important work in the theory of Fourier series back in the, I think, early 1800s. So we're going to define k sub n of x to be equal to the sum from minus n to n, of just e to the inx with no coefficients, right? Or the coefficients are all equal to 1, right? And so I'm going to write a little proposition. So I'm going to define the convolution, which we saw in a previous homework assignment. And so I'm going to look at the convolution of my function f with the Dirichlet kernel. Right, and so by definition, this is equal to 1 over 2 pi times integral from minus pi to pi of f of x minus y times kn of y dy, right, as we saw in a previous homework. And so the proposition is that this is actually equal to my partial sums, right? So the convolution of f with this Dirichlet kernel is equal to the nth partial sum of my function, Fourier, partial sums for the Fourier series of my function. Right, so this is a very important result, which is what we're going to kind of use in a very strong way to get the convergence theorem. Okay, and so this is going to be a consequence of the calculation we just did and the uniqueness theorem. So let's go through that. So the proof. Well, let me break it up into 2 steps. So the first step is let's just calculate the Fourier coefficients of the convolution, because I want to try to use the uniqueness theorem. So it helps to it would help to show that these 2 things have the same Fourier coefficients. Right, so I'm going to put a big hat over the convolution, and I'm going to let this at n denote the nth Fourier coefficient of this function. So remember, so this is maybe when you're first learning this stuff, you have to learn how to keep track of lots of different related but potentially distinct occurrences of similar objects. Right, so here we're looking at the convolution of my function with this particular kn of x, which is this sum over here. And what I want to do in step 1 is calculate the Fourier coefficients of this particular function, which is a different function than the other functions we've considered, at least appears to be different based on this definition, right? And so, well, this is just still a function of x, so I can calculate its nth Fourier coefficients, and so this is what we're doing now. Well, remember, we had this result in the homework problem related to the Fourier coefficients of convolutions. And in particular, we showed that the Fourier coefficient of this convolution is just the product of the coefficients of the 2 respective functions, right? So if you look at this Fourier coefficient, this is equal to the Fourier coefficient of f, the nth Fourier coefficient of f, times the nth Fourier coefficient of the Dirichlet kernel. Right. So what are the coefficients of the, I mean, we're assuming that the Fourier coefficients of f are given to us because this is the function that's been fixed. Well, what are the Fourier coefficients of kn, right? Well, we can just read these off from the definition of the kernel. Right, so let's just come back over here. This is our kernel. Well, the coefficient, the nth coefficient, let's just look at this. Well, if n is between minus capital N and capital N, it's just equal to 1. Right? And otherwise, all the other exponential terms for the Fourier series vanish. So the coefficient is 0, right? So the nth coefficient is equal to 0 if little n is outside this range, right? If you don't believe me, you can also just pause the lecture and try to calculate as we did in the last example. It should be a good exercise. So if this is a little confusing, again, I would recommend pausing the lecture, do the calculation for yourself. And if you get stuck doing this, then feel free to ask me about it, and I'd be happy to elaborate in more detail. So what this says is, well, what's the nth Fourier coefficient of our kernel? Well, it's equal to 1 if n is between negative capital N and positive capital N, and 0 otherwise. Right? And so this tells me that, or tells us that this formula here will be 0 unless n is in this range, right? Because outside the range minus n to capital N to capital N, this term is always 0. And so we're only seeing non-zero results if we're in this range between minus capital N and n. And so this tells us that, well, let's look at the Fourier coefficient of the convolution of our function with the Dirichlet kernel. Well, this is equal to, well, let's suppose that n is between minus capital N and capital N. In this case, I replace this value by 1. And so I'm just left with f hat of n times 1. And so this is just equal to f hat of n. Otherwise, I replace this term here by 0, right? And so it doesn't matter what f hat of n is. F hat of n times 0 is 0. So this is equal to 0 if n is outside this range. Okay. But this is exactly the same thing as the Fourier coefficients we calculated for the partial sums, right? So it's the same formula I have here. I just replaced little n by little m, but that's just notation, right? It's the same formula. And so therefore, this is equal to the Fourier coefficient of my partial sum, the nth Fourier coefficient of my partial sum. Great. And so this is kind of the key point that they're equal. And so, well, what do we do now? We just use the uniqueness result, right? So step 2, this shows that the Fourier coefficients of the convolution of my function f with the Dirichlet kernel are equal to the Fourier coefficients of the partial sum for all n. So by uniqueness theorem, the functions have to be equal. And so that's the proof. And so, well, let's sort of collect where we are. We're trying to show, let's just go up here. We're trying to show that the sequence of partial sums Sn of x, where these are partial sums for the Fourier series, converge pointwise to the function f as n goes to infinity. What we've done here is rewrite the partial sums into something, into this convolution object. And so this convolution object turns out to be easier to work with because it involves a certain integral, and we can calculate in a little bit. We can analyze it more precisely than we can analyze in this form. And so that's what we're going to do now, right? And so in particular, we can replace Sn of x by this. And so it now suffices to show that if I look at the difference between f of x and this convolution for each x, that this goes to 0 as n goes to infinity. Right, well, let's write out the definition of what this is. This is the absolute value of f of x minus 1 over 2 pi times integral from minus pi to pi of f of x minus y times kn of y dy. So here we're going to introduce a little trick, which has actually, I think, shown up previously a few weeks ago in one of the homework assignments. Well, notice that if I look at f of x, well, I have an integral here, right? And I want to relate this integral to this function. I'm integrating with respect to y, and this is a function of x. Well, I can write this as, this is like a constant with respect to y, right? So let me just write down a certain integral. Let's say I integrate minus pi to pi of 1 with respect to y, right? And let's say I look at this integral with dividing by the length, right? Well, this is just equal to 1, right? Because if you integrate 1 between minus pi and pi, you get the length, which is 2 pi divided by 2 pi, right? And so this tells you, well, f of x is equal to f of x times 1. right? So f of x is equal to 1 over 2 pi times integral from minus pi to pi of f of x dy, right? The key point is that, well, I'm integrating with respect to y, so this function, or this value f of x is like a constant, so I can just factor it out, right? And then once I factor it out, the integral evaluates to 1, and you get f of x is equal to f of x, right? So this is why this is true. And so if I plug this in, this tells us that we want absolute value of 1 over 2 pi integral minus pi to pi of f of x dy minus the same integral, but now the convolution terms. Right, we want this to converge to 0. But now I'm integrating over the same domain with respect to the same variable, so I can combine these terms. And so let me actually simplify this a little bit, right? In particular, we want to show that the 1 over 2 pi times integral from minus pi to pi of f of x minus y times kn of y dy, we want this to converge to 0 as n goes to infinity. Right, so all the analysis we've done so far shows that this would suffice to prove the pointwise convergence of the Fourier series, assuming certain hypotheses about the function f, which will allow us to actually make this work. And so now what is the problem? Well, kn of y, what is this equal to? This is this kind of complicated sum of exponentials. Right, so how are we going to understand this? Right. We better be able to understand this, or else we're wasting our time trying to work with this Dirichlet kernel, right? There's a reason why we've introduced this. So it may help if I rewrite this in a certain way. So let's pick a letter. Let's say, let's let z equal e to the iy, right? Well, this means that e to the I ny is z to the power n, right? And so therefore, kn is equal to now the sum from minus n to n of z to the n, right? But let's say we just looked at one term, like, or one half of this, like say n equals 0 to n of z to the n, right? So this is a geometric progression, or a geometric series, and we know how to evaluate geometric series very precisely, which you would have learned in an earlier calculus class, right? And so let's make this a little bit more explicit, and we'll actually be able to, we'll see that we'll actually be able to calculate what kn of y is equal to in a more tractable form. So this will be the next section. Right. And so as before, let's let z equal, z is equal to e to the I n y. And so, or sorry, e to the iy, excuse me. And so e to the I n y is equal to z to the n. So kn of y is equal to the sum from minus capital N to positive capital N of z to the n, right? And so what does this mean? Well, I can write this as z to the minus big N plus z to the minus big N minus 1, and so on up until I hit z to the minus 1. And then I have z to the 0, which is just 1. And now I have the other n terms, right? Z to the 1 plus z squared all the way up to zn, right? And what I'm going to do is I'm going to factor out the z to the minus n term, right? So I'm going to factor out z to the minus n. And if I do this, well, I'm left with 1 for the first term. And then I have z for the second term. I keep going, then z squared. And you can check if you consider the algebra that, well, this is going to keep going until I hit z to the 2n, right? Because if I factor out negative n from this, I'm going to end up with a 2n, right, at the end of the day, right? And so as I've said many times during the lectures, right, if this is just an algebra calculation, so if you're not sure what's going on here, you should pause the lecture and try to write it out for yourself. I think that would be a helpful exercise to double check this if you can't see it now. It's okay if you can't see it now, but you should pause and try to check it yourself, and hopefully you should be able to understand it, this factoring. Okay, well now let's plug back in the definition of z, right? So this tells us that kn of y is equal to e to the minus I n y, capital Ny, and then I have this geometric progression. Well, from the theory of the geometric series, we know that this is equal to 1 minus z to the 2n plus 1 divided by 1 minus z. And so I'm going to plug this in here. Right, so I have 1 minus, well now z to the 2n plus 1 is e to the 2n plus 1 times I times y. Right, and then I have divided by 1 minus z, so divided by 1 minus e to the iy. Right, and so now let me multiply this term on the outside through. So this ends up being equal to e to the minus I n y minus e to the iy, or what? E to the I times n plus 1 y. Right, because here I have a negative n, and here I have positive 2n, so one of them will cancel out, and so I just end up with n plus 1 times y divided by 1 minus e to the iy. Right. And so what I want to do is use the fact that we have, right, so this should remind you I have a complex exponential minus another complex exponential with alternating signs in the powers. So remember, we have a formula for sine of some angle involving a difference of complex exponentials. And so the idea now is to try to manipulate this fraction a little bit so that we can use that formula for sines, because then we're going to be able to express our Dirichlet kernel in terms of certain trig functions, which are a little bit easier to work with when analyzing the integral from before. And so what we're going to do is, for the sake of symmetry, we're going to multiply this on the top and bottom by the same thing. So we're going to multiply on top and bottom by e to the minus I y over 2. Right? So if I multiply through, what do we end up with at the end of calculation? So in the first term, I have e to the minus I and plus 1/2 times y. And then I have minus e to the I and plus 1/2 y, right? Because I'm subtracting 1/2 from negative n, so I get negative n plus 1/2. Here I'm adding negative 1/2 to n plus 1, so I get positive n plus 1/2. And then I'm dividing by, well, I do the same thing on the bottom, so I get e to the minus I y over 2. And then minus e to the I y over 2. Right. And so now here we're going to use the following trig identity, right? Remember, e to the I theta minus e to the minus I theta is equal to, or divided by 2i is equal to sine theta, right? Or I can move the 2 i's over, right? Right. And so I'm going to take this identity and plug it into both the numerator and denominator in this expression. I mean, notice that in both the numerator and denominator, we have something like this, right? And so now if I use this identity, we end up with, in the numerator, we get negative 2i times the sine of n plus 1/2 times x. And then in the denominator, we also get negative 2i times sine of 1/2 x, or sorry, y. Right. And so these negative 2i terms cancel out, so we end up with sine of n plus 1/2 y divided by sine of 1/2 y. Right. And so we proved the following theorem. Which is, if I look at the Dirichlet kernel at point y, this is equal to n scale n, right? The nth Dirichlet kernel, this is equal to sine of n plus 1/2 y divided by sine of y over 2. Okay. And so now let's plug this back into our original quantity. Right, so remember we were looking at the difference, or the integral of this, the difference of f of x minus y times this Dirichlet kernel. And we want to show that this whole thing converges to 0 as n goes to infinity. And so let's plug in this definition. Right, we want to show that the limit as n goes to infinity of absolute value 1 over 2 pi integral minus pi to pi of, well, you have f of x minus y minus f of x times the Dirichlet kernel, which is now we'll write in this way. We want to show that this limit is 0. And so if we can show that the limit of this integral is 0 as n goes to infinity, this will suffice to prove the theorem, right? Right, because we've, via a series of steps, we've reduced the pointwise convergence theorem to this fact here, right? Okay, and so in order to proceed, we want to look at the first term here. And remember, well, this is, look at this function, sine of n plus 1/2 over y. So this should remind you of like a sine Fourier series terms, right? And so in particular, these should remind you of, if you think back to a few weeks ago, these look a lot like the eigenfunctions for a certain boundary value problem, as we discussed before, like going in more depth into Fourier series. And we'll remember that as you varied capital N, these functions had some kind of orthogonality property. And so you may hope that, well, maybe we can take advantage of this orthogonality result for these functions. And so this is actually how the proof is going to proceed. And in order to take fuller advantage of this, let's define a function which I'll call g of y. Let's say g of y is equal to f of x minus y minus f of x divided by the other sine term. Right? And so with this definition, we want to show that absolute value integral 1 over 2 pi minus pi to pi of g of y times sine of n plus 1/2 y dy converges to 0, right? But now this looks like a lot like some kind of generalized Fourier coefficient of g with respect to these new orthogonal functions, right? In the sense that I reviewed at the beginning of the lecture today. And so, right, so we have the following fact. So the functions xn equal sine n plus 1/2 y dy, or not dy, sorry, just this. These are orthogonal on minus pi to pi. Right, and so in particular, if I look at the inner product of xn comma xm, you can show that this is equal to 0 if capital N does not equal capital M. And I think it's equal to 2 if they are equal. Right, and so if you divide by 2, then we have like the true orthonormal property discussed before. Right. And so this is just a calculus computation, which is very similar to a lot of the calculations we did when we were thinking about these eigenfunctions, right, and trying to understand sine Fourier coefficients. And so I'd recommend maybe pause the lecture and check this. It should only take a few minutes because it should be very similar to calculations we've done previously. And so what we're going to do now is just use this fact to try to conclude the theorem. Right, and so I'm just going to go all the way back to the beginning of the lecture today. Let's scroll up. Right, remember we had this generalized Bessel inequality. And so the Bessel inequality says, well, let me replace this by G, right? So if you have some collection of orthogonal functions in the sense described below, then we have this estimate for the infinite, for the sum of these terms squared, right? But we're working with something that looks a lot like the inner product of G with xn, where xn is defined to be sine of n plus 1/2 y, right? And G is our function G. And so if we can show that our function G has finite norm, then we can conclude that this series converges, right? Why does it matter that the series converges? Well, the only way the series can converge is if each of these terms goes to 0 as n goes to infinity, right? And so now let's take advantage of this observation. Right, so by the generalized Bessel inequality, if you look at the sum from n equals minus capital N to capital N, take absolute value and you take the inner product of the function G with x sub n, or sorry, this should be just minus infinity to infinity, squared. Well, if we know that our function G has finite mean square or finite L2 norm, then this is always less than or equal to this quantity. And so in particular, well, if you know an infinite series converges, the only way this can happen is if the terms converge to 0, term-wise, right? So in particular, this implies that this inner product squared converges to 0 as n goes to infinity. And so this tells us that inner product, right? So that's actually what I wanted to point to, right? Well, what is this equal to? What is the inner product of G with xn? This is the integral G of y times sine n plus 1/2 y dy times 1 over 2 pi from minus pi to pi, right? So this implies that this converges to 0 in absolute value. But that's exactly what we need to show in order to prove the pointwise convergence, right, of the Fourier series, right? And so you may think, okay, well, we're done, right? That's it. Well, we're not quite done because we need to show that this function G has finite L2 norm. Right? We need to show this quantity is actually finite. where remember, G is defined to be this function, right? And in particular, G depends on the point X that we fixed, right? And so what we're going to do at the beginning of the next lecture is just verify that this function indeed has a finite, the integral of this thing squared is actually finite under certain hypotheses about the function f. And then, well, whenever we can show that this function has finite square integral, in any of those cases, the Fourier series will converge to f, right? So we'll complete the proof of the theorem. Right, so we'll pick up there next time.